Most of our space infrastructure sits right next door in low Earth orbit. To find the next destination, you have to look far further out. Humans have not ventured into deep space or walked on the lunar surface since Apollo 17 in December 1972. The Artemis 2 mission will test a flight path designed to break that boundary. The spacecraft will follow a free return trajectory, looping past the far side of the Moon at a distance greater than Apollo 13 before swinging back to Earth. NASA astronauts Reed Wiseman, Victor Glover, and Christina Koch, along with Canadian astronaut Jeremy Hansen, are the crew tasked with testing this deep space architecture. NASA already flew this specific rocket and capsule combination in late 2022 on Artemis 1, but that test flight was uncrewed. Placing 4 humans on top of a launch vehicle drastically narrows the margin for error. Safely moving a pressurized habitat through the vacuum of deep space depends on the performance of a super heavy lift vehicle. To see how that scale is achieved, we have to break down how the world's most powerful rocket is built from the ground up. Fully fueled on the launch pad, the Space Launch System, in its initial Block 1 configuration, weighs 5.74 million pounds. The 2 5-segment solid rocket boosters flank the vehicle. Igniting for 2 minutes, they produce 75% of the 8.8 million pounds of thrust required. The attached core stage holds 2 tanks with 537,000 gallons of liquid hydrogen and oxygen. That liquid propellant feeds directly into 4 RS-25 engines at the base. These are repurposed legacy hardware, the exact engine models previously used as the main engines on the space shuttle. Escaping Earth's gravity well requires massive, sustained force. Combining these proven shuttle-era engines with larger, upgraded solid boosters provides the exact mathematical thrust needed to throw heavy payloads into deep space. After the initial climb, the boosters and the core stage exhaust their fuel and detach. What remains is the Interim Cryogenic Propulsion Stage, or ICPS, which fires its single engine in low Earth orbit. This graph shows the vehicle's velocity during a maneuver called translunar injection. As the ICPS engine fires, the speed spikes past 22,670 miles per hour, generating the momentum needed to break out of Earth orbit. Sitting just above the ICPS is a narrow ring called the Orion Stage Adapter. This ring serves as a specialized cargo bay, housing a secondary science mission of shoebox-sized satellites called CubeSats. Developed by international partners, these small devices will be ejected into the void along the route to measure radiation levels and study space weather. By utilizing this adapter space, Artemis 2 acts as both a transport vehicle and a mobile deployment system for deep space observation. At the very top of the stack sits the Orion spacecraft. While the capsule has flown before, this 10-day trip is the first time its environmental control and life support systems will operate fully active with a human crew relying on them. The Archer study shifts the focus from the machine to the passenger, monitoring how human biology handles the stress of deep space travel by tracking cognition and teamwork. Each astronaut will wear a continuous monitoring wristband, recording their daily movements and sleep quality as they work far away from Earth. They will also face high-energy solar particles. Once the capsule leaves the protection of Earth's magnetic shield, ambient radiation levels rise, testing the physical shielding of the hull. Delivering a capsule to the Moon requires a massive rocket, but the true pass-or-fail metric of the mission is whether Orion's interior hardware can keep 4 people healthy and alert through a 10-day round trip. Every future plan to explore the inner solar system requires the data gathered on this 10-day flight. NASA has to validate emergency abort operations, test rescue procedures, and prove that the life support systems can sustain astronauts over long durations. Once those specific mechanisms are confirmed, the agency can clear the launch of Artemis 3, the mission designed to put humans back on the lunar surface. The Artemis program is shifting our relationship with the Moon from a static, historical destination into an active presence. The scale of the SLS and the systems tested here serve a specific long-term purpose, building the reliable hardware necessary to eventually launch a crew to Mars.